Unit Operation Classroom, we're going to discuss how to find minimum reboiler duty in a distillation column. My name is Shekhar Bhattacharya. A continuous distillation column is used to separate an equimolar mixture of diethylamine and methanol. Okay, so binary system. The feed enters the column as saturated liquid. Remember that at a flow rate of 30 mole per second. It is desired to obtain 90 to 1% diethylamine as distillate. So distillate concentration is given. The rate of withdrawal of the distillate is also given, that is 10 mole per second. The equilibrium curve is given. So we have to find out what is the minimum reboiler heat duty. So let's look at the schematic diagram here. This is my feed, which is a mixture of diethylamine and methanol, and it's an equal mole fraction. So we've put that as 0.5 equimolar mixture, and it is a saturated liquid. And the distillate flow rate is 10 mole per second, and its concentration is 92 mole percent diethylamine. So this is very simple. We can find out the bottom's flow rate and the concentration of DEA. Here, XP is 29 mole percent DEA. That is very simple. So we have found out that. So we have to find out what is the QR minimum. That's a minimum boiler rate within the reboiler. Okay. So let's draw the Machiavelli diagram, very standard. This is my diagonal line here, and this is the equilibrium curve which is given. So what we have to do, we said feed is a saturated liquid, therefore Q is equal to 1. So wet line is going to be vertical at 0.50. For minimum reboiler duty, we have to find out the minimum vapor boiler rate, which happens at minimum reflux. So minimum reboiler duty here. Okay, so this is the minimum boil up rate we have to find out, and that of course happens when there's a minimum reflux or minimum. So the problem essentially reduces to find out first the R minimum, the reflux ratio. All right. Also, the rectifying of course section operating line starts at XT and XT. This is very standard, 0.92, 0.92, and passes through the intersection point between the feed line, Q is equal to 1, and the equilibrium curve. So basically, what we have to do here, as you can see, so this is my, first we identify this point. This is 0.92, 0.92, XT, XT here, and this of course is XP point. This point is XP, which is 0.29, 0.29 here. Okay, and this is the feed line here. Q is equal to 1 because this is a saturated liquid. Q is equal to 1 and 0.50. So this goes here, and this intersects the equilibrium line here. Okay, which is 0.50, 0.60. So this is 0.50, 0.60. So for R minimum, we know we have to draw the rectifying section operating line. So basically, it's a pinch point. So we have to find out draw the straight line between XT, which is between 0.9292, and this pinch point here, which is 0.50, 0.60. So this is my rectifying operating line. And we can easily find out the slope of this rectifying operating line because we know these 2 points, which is this one and this one. Okay, and from there we can calculate the R minimum. So let us do that. Slope of the rectifying operating line is calculated. So this is between 0.9292 and of course 0.60 and 0.50. So this is the slope. We know the rectifying operating line equals, so this is the slope of the rectifying operating line, and this is the intercept. So slope we have found out 0.762. So we can easily find out our minimum from there, which is 3.2. Now, if on 3.2, we can all find out the molar liquid flow rate, which is of course is equal to L is equal to R. So this is equal to R minimum into D. So this is 32 mole per second. So liquid flow rate, and vapor flow rate of course is equal to L plus T, because we know here, if we take any plate here, so let's say if we take any plate, if this is equal to L and this is equal to V, and if we do the material balance, we can say, of course, V is equal to L plus T. So we do that. We know the value of L, we know the value of T, so that's 42 mole per second. So the vapor flow rate at any point within the rectifying section is that 42 mole per second. Now, since the feed is a saturated liquid, it adds up to liquid flow in the stripping section. So here, uh, since this is a saturated liquid, so just goes down directly into the stripping section. So whatever there is a vapor flow rate here in the rectifying section, thus must be equal to the vapor flow rate in the stripping section. So V bar is equal to V. We already found out V. So assuming this is R minimum, so we can therefore say that is equal to V bar, which is equal to 42 mole per second. So this must be the minimum boiler rate. So if we just multiply this one multiplied by lambda, that will give me the heat duty. So this is what it is. So we said vapor flow in the stripping section, V must be equal to vapor flow in the rectifying section. So V bar is equal to V, that is equal to 42 mole per second. That's a vapor boiler rate. So minimum reboiler duty is multiplied by lambda, that's to 1470 kilowatt. Additional information. Minimum reboiler duty heat duty can also be calculated using the stripping section operating line. So here we have found out the value of the minimum reboiler duty using the material balance and the component balance on the rectifying section. So using the Mackey-Thiele diagram operating line. However, we can also find out the reboiler heat duty. The minimum reboiler heat duty is in the stripping section operating line also. Let's see how we can do that. We know this is the equation of the stripping section operating line. This V bar, of course, is the boiler rate from the reboiler. So this is my slope, and this, of course, is the intercept. Okay, so from the curve, from the graph, Mackey-Thiele diagram, if we can find out the slope of the stripping section operating line using the 2 points xb and x dash y dash, which is the pinch point 0.50, 0.60. Let's look at here. So this is the point 0.29 xb 0.29, 0.29, and this is my pitch point, which is 0.50, 0.60. So we can use this data to find out the value of the V bar. So you see, this is the value of the slope of the stripping section operating line. Now, of course, L bar is equal to V bar plus B. This is L over bar, and this is V over bar. So if we just do the material balance, as you can see, L over bar is equal to V over bar plus B. So that's what we were seeing. L over bar is equal to V over bar plus B. Uh, we know this L over bar, which we can find out from the slope, because this is equal to L over bar by V over bar. So from here, we can find the value of V over bar. All the details are given here in this website. So you can see this V over bar is equal to 42 mole per second. So this value is exactly the same what we find out from the rectifying line operating section. And of course, the value of QR minimum remains the same, is V bar over lambda. So this value is the same value what we have obtained from the rectifying operating line solution here, which is 42 mole per second. Okay. All right. So these are very standard and simple uh, uh, features of McCabe diagram. Now let's see a practical application of this problem. This particular lidocaine is local anesthetic, involves synthesis of an intermediate of this one, which is an acetamide, and this is the actual IUPAC name of this one. So the amide intermediate is subsequently reacted with diethylamide to produce lidocaine base. So if we just react with DEA, we get the lidocaine base here. The amination step results in a light organic recovery stream containing unreacted DE and methanol. So a recovery column can used to separate the same as the DEA leach overhead stream, which is recycled back to the amination reactor as the methanol stream. Anyway, so the given problem tells us that the required separation, that's a minimum reboiler heat duty, is 1470 kilowatt. Actual rebellion is of course going to be higher than QME because R is of course greater than R minimum. This gives us the estimate of the steam requirement of the reboiler and overhead condenser sizes and total energy cost. So going back to the problem statement here, of course, D is the correct option.